Hi, my name is Shahir Ashramian. I direct the ASIC research group here at Nokia Bell Labs. And I want to talk to you a little bit about the technology that we're working on to enable the next generation of point-to-point communication links. Now, it is no surprise that we want to constantly go to higher frequencies. There is so much bandwidth available, especially above 110 gigahertz, allowing us to reach speeds as much as 100 gigabit per second. At the same time, the size of our antennas will shrink. All of these are great advantages for deployment scenarios. But of course, there are also problems. We need a new generation of integrated circuits to be able to operate at these frequencies and give us adequate performance. But even beyond that, we need to go past traditional PCB and packaging materials. Otherwise, the performance degradation that classic materials have on these frequencies is just too high for these devices to have any practical deployment situations. As a result, we moved into an entire new generation of materials called radio on glass, where we actually place our internally developed RFICs on a glass substrate. This glass substrate does a lot more than just packaging our devices. It allows them to interconnect with each other. It allows us to incorporate things like filters and power combiners and diplexers and a variety of transitions, including waveguide interfaces, which then can go into traditional dish antennas. The performance we can get from this glass material is above and beyond anything we can get from printed circuit boards. And all of the millimeter wave and near terahertz signals are encapsulated within the glass substrate, which means it makes it quite easy to drop into a product because you don't have to worry about how you affect the performance of the millimeter wave near terahertz signals because none of it leaves this glass module. At the same time, we can take this even a step further. We can create hundreds of antennas on our glass substrate and create a two-dimensional beamforming phased array operating above 110 gigahertz. Now this all of a sudden creates situations where you can create a mesh network in the future at these frequencies and at these very high data rates, or do point-to-point links which are self-aligning. As things move around, because you have a beamforming structure, you can realign the antennas and avoid having to have someone go and realign the antennas every time something goes wrong. These are pretty exciting developments using this material, and these will eventually find their way into our products into the future. And what we have next to me here is a live D-band link, miniaturized for a tabletop setup. We have a beam across two of our modules, these modules that I'm holding here, and I can of course disrupt the beam by putting my hand in front of it, and you can see that the constellation disappears. These modules are appropriately designed to couple with some dish antennas to go hundreds of meters, potentially above a kilometer, depending on the deployment scenario. And I hope that you enjoyed this brief presentation about the Nokia Bell Labs radio on glass technology operating in the D-band frequency range, enabling next generation point-to-point radio links.